Hi, everybody. Welcome to Lecture 14. Woohoo! We're almost halfway there. That's amazing. Okay, and we're about to tie up a lot of loose ends in Chapter 8, and that's also amazing because everything we've been doing so far is all about SN2. Everything's SN2. And as you'll see after today's video, there's a reason why we love SN2. But today's PowerPoint is brought to you by, oh my God, the biggest thing possible. Are you getting bored of my animations? I hope not, because I got lots of them. I got lots of animations. I haven't even started yet. So keep in mind that there will be a little bit going on about leaving groups today. They'll play a big role in what we're doing today. And so, oh, wait, where's my mesylate? Oh, there's the mesylate. Okay, got it. And the tosyl chloride, yep, you see that? Okay, those are very good leaving groups for our alcohols that are going to be part of our reactions today. So hopefully by the end of our class today, you'll be able to tell me why one of these carbocations is a bad cation. Okay, so I'm going to throw this on a Jamboard slide and see if we can make sense of this cartoon. And yeah, let's do that. Okay, all right, let's dive back in. So we just finished looking at SN2. So now what's the whole story? Whoops, what happened here? Oh, I lost an animation. So that's okay. I'll be the animator. Woohoo! Okay, so let's go look at what this reaction is all about. The one that doesn't even need the nucleophile. And the one that we've talked about in the past, this is the SN1 reaction mechanism. And so what's actually taking place during this mechanism? So that's what I've been teasing you with this slide. What's the reaction SN1 mechanism? So one of the things that you want to keep in mind with this SN1 reaction mechanism I'm about to show you is that yes, it takes, and this is the confusing part, the whole synthesis of this nucleophilic substitution takes 2 reaction mechanism steps. But we only call it one, SN1, because you have to do one thing at a time. Corny, maybe, but helpful. And the one thing that has to happen that's more important than any other step in this reaction mechanism is the leaving group has to just fall off. So this is the rate determining step. This next one is really fast, and that's the one where the nucleophile will attack this carbocation. But this first step is the rate determining step. It's the slowest one. It's the one that can control the whole process. So this is why our rate law has only the T-butyl chloride in it, and therefore this is why it's called an SN1 reaction. Okay, so as always, I have our British friends to help explain this reaction mechanism. I love the little echoey stuff. Okay, have fun listening to this. Here's the link in case you want to watch it over and over and over again, like my wife does with Downton Abbey. Oh my God, shoot me. Okay.
Tertiary halogenoalkanes undergo SN1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenoalkanes, the small hydrogen atoms in primary halogenoalkanes are replaced by bulkier alkyl groups. Tertiary halogenoalkane. The bulky alkyl groups do not allow attacking species to approach the central carbon atom. Consider the reaction between 2-methyl-2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenoalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with the nucleophilic hydroxide ion via a second transition state to form the product 2-methyl-propan-2-ol. Transition state, carbocation, EA2. SN1 reactions.
So please watch that as many times as you want. I can never get tired of the echoey stuff. I apologize for the little scribbles. We were going to watch it as much as... Okay, sorry. Maybe we are going to watch it as much as you want. I want to watch it again. No. Okay, so I apologize for the scribbles that showed up on top of it. So please feel free to go to this YouTube link and watch it at your leisure. And notice a few things that were important about this SN1 mechanism. This carbocation intermediate that he kept talking about, did anybody notice that it was planar? So when you only have 3 bonds on that carbon, how it all turned planar. And we're going to look at that in the impact of that. That's very unique, especially when it comes to all the stereochemistry we've been playing with. Okay, and that really he used OH minus as his nucleophile. And that OH minus is a really great nucleophile. But even a great nucleophile like OH minus cannot attack, as he mentioned, a big tertiary aliphatic carbon. So first and last name, too bulky, can't do SN2 this way. So can't do it. So the only way our OH minus or our negatively charged nucleophile can attack this tertiary carbon is if it waits for the leaving group to fall off. And we'll take a look at this. Okay. Oops. Wait. Oh, sorry. So if you're going to get the leaving group to fall off and form this carbocation, it's very important that we try to stabilize it. And therefore, the more reactive SN1 reactions, the ones that are going to go SN1, are the reactions that can create very stable 3-bonded carbons. So here's the story with 3-bonded carbons. They have this empty p orbital, and again, here is that planar portion. So I want you to just keep this in mind. But this one has 3 methyl groups attached to it. Big methyls, tons of electron density around here from all these CH bonds. Tons of methyl groups that are nearby this empty p orbital. And so what does electron density, partial negative charge, electron density do when it's nearby an empty p orbital? You guessed it, hyperconjugation. A little borrowing of electron density, similar to what we saw with allylic and benzylic reactions in SN2, that they weren't doing resonance. Not resonance, because there's no way to break these bonds. But if I have these sigma bonds that are kind of right next to on carbons, then I can start donating, and I apologize if the picture's a little blurry, so please stop and look. But notice these bonds here, these CH bonds. If it's a primary carbon, I can donate a little bit of this CH electron density bond into that empty p orbital. But notice if there is no CH, if I just have hydrogen sticking straight out, there's nothing for me to borrow electron density from. So it's not surprising that as you start putting more and more carbons on your carbocation, on your electrophilic carbon, like this tertiary carbocation, you are going to get a lot of hyperconjugation from all the CHs that are nearby this tertiary carbocation. And therefore, this is going to be the happiest carbocation you can possibly form, and this primary carbocation will never form because it just can't get enough electron help from the hyperconjugation. Okay, let's keep playing with this. How does this influence stereochemistry? If I just pop off the leaving group and create a planar 3-bonded carbocation. So let's take a look at this. Here's an example where I have, let's give a first and last name to this guy. What is that? Electrophilic carbon. Wait. Did you say secondary is the first name? I agree. Second. Did you spy that that's a benzene ring for pH? And that's a carbon that's almost in a benzene ring? That means it's benzene-like. This is a secondary benzylic. Which usually loves to do SN2 chemistry. But notice in this reaction, there's a big, huge, huge problem. How strong is this nucleophile? Is it a strong base? Yeah, let me react. I love positive charge. I can't wait to react with positive charge. No. So here's the other piece about SN1 reactions that's going to come to fold is what if you do or try a nucleophilic substitution and you have a very, very weak nucleophile? Sure, it has partial negative charge here, but it's not fully negatively charged. So another impetus besides steric bulk around the electrophilic carbon that makes backside attacks impossible for SN2 is weak nucleophiles do not want to go SN2. So what are they left to do? They're left to sit around and wait for an SN1 carbocation to form. So that's what has to happen in this first step is Cl just has to fall off. And then water can't push it off from the backside, even though it's a secondary benzylic, which would love to do SN2. But it's such a lousy nucleophile. No SN2. So for SN2, I need both a strong nucleophile and an unhindered electrophilic carbon. For SN1, as soon as I start getting more substitution around the carbons, secondary, tertiary, it gets harder to do SN2, but it gets impossible to do SN2 if I have a poor nucleophile. So a poor base, like water. So water can act nucleophilic here, but it has to wait to form the carbocation. And now, as you saw from the previous slide, I just turned the carbocation in the p orbital that was empty sideways at this point to help you see this backside front side attack. That really now, if I'm the water molecule, I can come from either direction on this planar achiral intermediate carbocation. So this water can come from either side. Why would it have a favorite side? So it doesn't have to do backside attack because the leaving group is gone. There's no more Cl. So the one thing I hate about SN1, and that we're going to try to avoid SN1 like the plague, and why I left it to last in this entire nucleophilic substitution process and had lots of lectures on SN2, because let's make sure we do SN, is because SN1 I lose all stereochemistry. None. That I become achiral. So notice, even though I started with S, a separated, purified, pure enantiomer, Hard to do. As soon as it went through an SN1 reaction, I lost all stereochemistry. It's no longer S. The carbocation is not S or R. And therefore, this water molecule can attack from either side. And it will. Equal chance. No benefits from acting from either side. And so the water reacts mechanistically. Do not lose the hydrogen until after the water reacts and uses one of its lone pairs, because then it becomes positively charged, and only then will this oxygen want to lose H+. So oftentimes you can see water is used here to grab this hydrogen. This is making H3O+. But really, I don't mind if you do the following, because that water is not a strong base. It's not really going to go grab that H+ off that molecule. What's really going to happen is the oxygen's going to grab this bond really tightly, and it's going to spit out, circle, and kick out H+. And yes, maybe some water will fall in love with it in solution somewhere. But in all honesty, that O+ is so uncomfortable. Where would you rather have the positive charge? On an oxygen or on a hydrogen? Right. So let's make H+. And so this is how we get to our final product. And what I want you to notice here, though, is we do get stereochemistry back, but I have a 50-50 mixture of these two stereochemical isomers. And that's not really that helpful. What we call that 50-50 mixture that went through, half of it did inversion, half of it just retained the same stereochemistry, meaning S went to S. Half of it went and did get inverted, like an SN2. But whenever we get a 50-50 mixture, this is called racemic. And this is awful, because you start with such a pure enantiomer and you end up with a mixture. Not only do you not only make just one, you make two different compounds, two enantiomers. Ugh, SN1 is the unspoken, nasty little nucleophilic substitution reaction that will only happen if you can't do SN2. So that might be the approach you take with every nucleophilic substitution. You see, can I make this nucleophilic substitution go SN2? Does it have a good nucleophile? Does it have a good leaving group? On an unhindered electrophilic carbon, SN2 is the way to go. And this is just the, like, if I can't do SN2, then maybe it'll go through this SN1 stuff that I hate so much. SN1. Okay. So here's another reason why I kind of abhor SN1 reactions, even though they exist and you need to know them, is because of this carbocation right here. What else can carbocations do in the middle of this whole process before this poor, weak nucleophile reacts with it? Chaos. So if you determine that you have an SN1 reaction, then that carbocation can go to different carbons, and the only reason it can move is because you've done an SN1 reaction that's made a carbocation. If you do SN2, it's all happening at once, backside attack. There's no time or full charge for anything to move. So it has to be SN1 to create this carbocation. And so this is a secondary, and I didn't put its last name in here, sorry, aliphatic, which is totally fine to do an SN2 reaction, but evidently I must have a poor nucleophile around, so it just couldn't. So the leaving group, the tosylate or mesylate even, just fell off, leaving this carbocation. And if you notice, this carbocation is right next to, this secondary, is right next to what looks like a tertiary. Ooh, we love tertiary carbocations. They're very stable, a lot of hyperconjugation. And so what can happen is this little hydrogen can take its pair of electrons and the H and jump one carbon over. Oh my God. This is called a 1,2 hydride shift. And there really is nothing, I don't know why they emphasize the 1,2, because you can't do a 1,3 hydride shift. You can't do a 1,4 hydride shift. So they're very, very rare. You can only do 1, 2 atoms apart and do a hydride shift. And this only happens if you can move that carbocation to the tertiary carbocation. So be on the lookout for these hydride shifts, and it comes from the name that when you move H and its pair of electrons, this is the name for a hydride ion, as opposed to a proton for H+. Okay? Very scary. Wait, if a hydrogen can jump one bond over to put the carbocation on a more substituted carbocation, can anything else jump? Like, can I get a whole benzene ring to move? If there was a benzene ring there, can a benzene jump to put a carbocation? There's only one other thing that can move. Hydrogen's small enough, it can jump. The only other thing that's small enough that could move is a methyl. So here I have a quaternary carbon. It's got 4 carbons attached to it, next to it secondary. So maybe I can get the methyl to jump. Oh my God, that means this entire methyl and its pair of electrons is wait, you need to see this. Here we go. Watch closely. Oh, wasn't that cool? Wait, come back. I went too fast. Okay, I like that. Let's go back. Isn't that cool animation? Okay, jump. And as the methyl's moving its bond over, it's breaking from the quaternary and forming a new carbon-carbon bond on what used to be the secondary. And now I have a tertiary carbocation, and that is much better than a secondary. So this will always happen. So now not only do you have to look for a carbocation and a poor nucleophile and determine its SN1, but as soon as you make your carbocation, please look around. Look next door, especially if you have a secondary carbocation. Can you move that secondary to a tertiary carbon next door? And it will do that if there's a methyl you can shift or a hydrogen you can shift. Then the nucleophile would attack here. So the water would then end up not on the original carbon like this one. Nope, it's not going to go there. This lone pair is now going to attack this carbon. And you will end up with an alcohol on the more substituted carbon. Very tricky. But if I ever give you a problem where you see the reactant has a leaving group on an electrophilic carbon, and you see I've given you the product, and the nucleophile is on the carbon next to the one that's nearby, or what other things can happen? Be on the lookout. I told you resonance was really popular. Wait, I got too excited. What if this carbocation was next to a double bond? Could I get the carbocation to move by resonance? Oh my God, I got resonance of carbocations, of course. So now these carbocations can move all over the place. They can move by hydride shift, they can move by methyl shift, and they can move by resonance. And all these movements will only take place if you're taking the carbocation and taking it from a less substituted carbon like secondary, and move secondary aliphatic even, and moving it to a more substituted, more stable carbocation like a tertiary aliphatic, or even a secondary benzylic or secondary allylic. Those are more stable due to resonance. So be on the lookout. That's all I can say. Oh, warning, warning, warning. SN1, look out for rearrangements. Oh my. Welcome. Now do you know why SN1s are not my favorite little toy? All right, so here's a summary of it. Again, we love the tertiaries, but notice I haven't given any last names to these. If I have the benzylics, they're better than the allylics, which are better than the aliphatics. And that is all due to resonance stabilization of the carbocation. That's something we learned back in the acid-base days. So in playing with resonance structures. Okay? Wait, there it is. Oh, you know, this looks like a 3-bonded carbon here. This little dude, he should have a frowny face. He's not happy at all. He's got a carbocation, but little does he know, a bromide is waiting to attack. And remember, this sort of looks plainer in this cartoon, but I think the artist had a little license with planar just to make it look scarier. Okay, so that's maybe what a carbocation is feeling like. And that's what maybe the nucleophile is ready to do once it creates the carbocation. Revisiting polar and aprotic solvents now, protic and aprotic. We talked about how aprotic solvents, the ones on the bottom here with all the acronyms, are great for SN2 reactions. Go back and review why, and why we hate these polar protic solvents for SN2 reactions, because they surround the charged nucleophile, like water, hydrogen bonding it. So here's a summary of that, and I've added a little bit to each statement. If I'm creating a carbocation that is charged, full charge, if you were fully charged, would you rather be swimming in a nice polar solution of water or a very non-polar solution of acetone? Wait, I need help. I'm a 3-bonded charge, help me. And the acetone would be like, sorry, dude, I have no real passion to want to interact with a charged molecule. I'm organic, neutral, and not very polar. But if you put the carbocation in a beaker of water, all the water is going to surround it and love it and stabilize it and make it feel less charged. And so for SN1 reactions, we really like these polar protic solvents if we can. And if you can avoid it, try to stay away from these aprotic ones. If you're trying for some odd reason to do an SN1 reaction and you want to show the reader you want it to be SN1, don't put an aprotic solvent into your reaction, because that's a signal that you want to do an SN2. So these are the solvent kind of plays a role in helping tell the reader what kind of mechanism you prefer. Oftentimes it has no outcome on the actual event. So take-home message about solvents. Their job is to dissolve everybody. That's flat out their job as a solvent. They will rarely dictate SN1 and SN2 because that depends on the strength of the nucleophile and the bulkiness of the electrophile. So those two are what really dictate whether you go SN1 or SN2. And hold on tight to those. Try not to give equal importance to all the other two parts. Leaving group and solvent are not nearly as important as the substrate and the nucleophile. Whew. Cool, a lot of talk there, sorry. So, summary of our SN1. Try to see that I'm going to do an SN1, and notice this is in a protic solvent. Notice this is on a tertiary carbon. And even though I have a good nucleophile, this is too bulky to do backside attack. So it's got to go SN1 and go through a carbocation planar intermediate. Okay, I haven't shown any stereochemistry in this one, but keep that in mind. So nucleophile is not present in the transition state. It's not present in the reaction, and therefore the strength of it does not impact. But really, you can see it really is in, I'll do SN1 more with poor nucleophiles. Or if I have a poor nucleophile and an electrophilic carbon that's not tertiary or secondary, then maybe I don't do any nucleophilic substitution at all. Poor nucleophile, poor electrophile, poor reaction, you don't get to go. You don't get to make a product. So, tert-butyl chloride's carbocation is the only thing seen in this reaction. It turns planar, it's unimolecular, then the nucleophile adds and creates this awful racemic mixture if you have a chiral substrate, meaning starting material. And in the small print, if you can put it in a polar protic solvent and get everybody to dissolve in that, you're going to favor SN1. No, okay. So have I downplayed SN1 enough? I don't really. All right. So let's put this to practice. Take a look at this. Ooh, I used a different exclamation point. Take a look at this reaction and tell me which of these answers, if any, actually are the final product from this reaction. This Me is an abbreviation for methyl. So always little new things that are going to come your way. And pay attention, this is a chiral starting material. So have some fun with that. Okay? This is also called sylvolysis, just to let you know. This is where I have taken the nucleophile and also made it the solvent, which means I have just put this alkyl chloride compound in a bunch of methanol, tons of it, and it's acting both as a possible nucleophile and as the solvent that the whole thing is swimming in. And that's why you see those like that. It's kind of odd, but sometimes you'll see it like that. So I'm glad I could show it to you. All right, and just so that we're not lost in SN1 world too long, I'd like to pull us back to the one preferred actual reaction mechanism we're going to try to use as much as possible is SN2, because you have a sense of control about where things go. I love this slide because I love for you to come to class with possible reactants and a solvent, all four parts of your nucleophilic substitution listed in your reaction. And to do this, you actually have to start thinking backwards. Like, what two pieces must have been present in the reactants up there that could come together in an SN2 reaction to produce those products? So, right, so, and those products down there. So you actually have to really dissect the products and pull them apart and play with them and think about what could be the nucleophilic part, what could be the electrophilic carbon part, and try to put them together and even pay attention to stereochemistry. Whew. You can do this, you rock. You're on your way to orgoland synthesis, where you can make anything you want. That is incredibly powerful if you want to make drugs, make cures for cancer, anything. Boom, it all starts on this slide. So I can't wait to see your answers on the Jamboard. I can't wait to see us play with these nucleophilic substitution reactions. And the next video will be a complete summary of trying to, again, put it all together. How do you recognize SN1 versus SN2? And that's what the next lecture video will be all about. Okay? All right. Have fun in Orgoland. Don't go into Orgoland alone. Play with your study group members. Come see me. Just don't do it alone. It's not fun. All right. See you soon. Bye.